Okay. All right. So then the other important cofactor we talked about was TPP, the thiamine pyrophosphate, right? And the idea here is that this carbon is reactive because of its proximity to this nitrogen. Um, Reactive in the sense that it can actually be deprotonated and form a stable ylide. So a stable carbanion that's reactive. This carbanion can then attack something, right? It can serve as a nucleophile to initiate a reaction that links our cofactor to our substrate. Okay, and this is typically going to happen with the carbanion attacking a carbonyl carbon, right? And that's what you saw in your activity on Tuesday, the kind of the last thing that we were doing. Right, so we'll see that. We'll see how that works when we talk about pyruvate decarboxylase. We'll kind of go through that mechanism quickly. Okay, let's first talk about dopa decarboxylase. Right, this is the one that uses PLP. Okay, and I'm showing here. So dopa. This enzyme decarboxylates dopa. Okay, and remember the way that all decarboxylation works is that we have the alone pair on this oxygen that forms a double bond between the oxygen and that central carbon, and this bond then breaks. And the idea is that these electrons in this bond right here have to go somewhere, and they have to go somewhere that's stable, okay? The value of using PLP here is that this being our alpha carbon, this being the nitrogen that ultimately is attached to our cofactor, right, that makes the shift base, if this bond right here is the one that's in the plane of the pi system, then it's this bond that's reactive. So these electrons in this bond right here are electronically linked all the way down to the nitrogen in our PLP cofactor. So kind of bear with me here. So this nitrogen is part of the shift base that's on our cofactor, and I'm not going to draw everything out, but I'll draw enough. Okay, so here's our cofactor. This would be NH, not NH3. Y'all are smart enough to kind of get that, right? Um, so then the idea is that the electrons, once we make this double bond, this bond breaks, the electrons flow in one smooth motion all the way down to our electron sink nitrogen. That then creates an intermediate where the nitrogen has a lone pair, it's neutralized, right? They're stably placed there. And we've lost our carbon dioxide. Okay, so we have effectively decarboxylated dopa. The next step is to release the cofactor, right? So what we want to do ultimately is to take these electrons and push them back up and do something useful. Okay, notice here on our product, dopamine, on what was the alpha carbon, it's sp3 hybridized, right? So there's two hydrogens, whereas right now, this carbon is sp2 hybridized, there's only one hydrogen. So what we need to do, what we need to think about doing, is picking up a proton from a general acid in our active site. So let's just expect that there's some general acid here. These electrons get pushed back up through our ring system, all the way back up to the pi system, and ultimately we pick up a proton from that general acid. These are the two really critical steps in this PLP mediated reaction, right? Anytime PLP is involved, the very first thing you should think is that our substrate gets covalently linked to the cofactor through the formation of this shift base, oh, not here, this shift base right here. Okay, and hopefully you remember from the last couple of days that this always happens by replacing a lysine side chain, right? Because the cofactor is always anchored in the active site through a shift base to a lysine in the active site. So our nitrogen right here simply reacts with the cofactor and replaces that lysine. Otherwise, the bond looks the same. And then once you've made that linkage, it's really about figuring out which bond to break, push those electrons all the way down to the nitrogen, look at your products, figure out what it needs to be, and then reverse the process, right? So we figured out that in our products, our alpha carbon is now sp3 hybridized, so we need to pick up a proton. So push the electrons back up through the pi system and pick up a proton. Okay, these are the two central key steps to PLP mediated reactions. Push electrons to the sink and then push electrons away from the sink to regenerate that positively charged nitrogen. Okay, we've seen two examples of this already, this L-dopa decarboxylase and then also the our transaminases. And we are going to see more this semester. Okay, so any questions about those? That's the big theme with PLP. All right. Pyruvate decarboxylase. This is an enzyme that uses the TPP cofactor, right? We're told here that the ylid form of TPP is a cofactor that's important in this reaction. And if you look at your activity, it tells you that this carbanion carbon from TPP ultimately reacts with our alpha carbon, and we end up with an OH here, right? So hopefully it's pretty easy to kind of gather that the way this works, I'm not going to draw the whole cofactor. This is our reactive carbon. This is the nitrogen. So hopefully it's pretty easy to kind of like imagine that the way this works is that we have a general acid in our active site. The ylid form of our TPP reacts with that, right? So that's the nucleophile. This is the electrophilic carbon. And we push electrons up and pick up a proton from our general acid, forming an intermediate where we have an sp3 hybridized central carbon, alpha carbon. And our TPP cofactor now has this electron sink right here, right? That's the important electron sink that we're going to use in our mechanism. Because ultimately, this is a decarboxylase. And remember, the theme with decarboxylases is we lose CO2 in the same way every single time. Find a carboxylic acid, the one that you got to get rid of. Take the electrons from the negative charge, make CO2, break a bond. And in this case, we now have a place to put these electrons. So we push the electrons all the way through our cofactor to our electron sink. One fluid motion for the electrons moving over to the electron sink in our cofactor. This is the case for each of these three forms of our electron sinks, whether it's TPP, PLP, or the Schiff base. We're always fluidly moving electrons to that positively charged nitrogen. That's the first critical step in breaking the bond. Okay, when we do this, we now have lost our CO2, and we basically have a version of this that is covalently anchored onto our TPP cofactor. So at this point, the product is not a double bond, it's a single bond there. So we have a lone pair there. We have a double bond between our cofactor and what is an OH and a CH3. Okay, so ultimately, we need to break both of these bonds right here, the pi bond and the sigma bond. And we can't do that in one step, right? We can't break two bonds in one step, so we'll do it in two steps. In the first step, we are going to protonate this carbon, right? So ultimately, we need to have a hydrogen here, and right now we don't. Right now, we don't have that hydrogen. So we're going to imagine that there's a general acid in the active site where we can pick that proton up. So let's show a general acid. Okay, and we're going to push electrons up through our cofactor and pick up a proton, giving us our final intermediate where we've regenerated the positive charge on the nitrogen. We have a single bond between our cofactor and what will be our product. And the only difference between our product, right, so what ultimately ends up being an aldehyde, and what currently we have is we have this alcohol. So hopefully it's fairly intuitive for you to see that we need to deprotonate that oxygen so we can make the carbonyl. And when we do that, we can push those electrons back onto this carbon to regenerate the carbanion. And then we've created our products. So let's do that. We have a general base, which is going to be what is produced right here, right? So this started as a general acid. It now has been deprotonated, so it's going to serve as a general base. We pull the proton off that oxygen, push the electrons down to make our carbonyl, and then these electrons end up making the negative charge, our carbanion, on our cofactor. And we have produced our product, and we are left with the original form of our cofactor. Okay, so in this case, the same theme applies. The theme is use the cofactor, use the nitrogen in your cofactor as a place to put electrons. Figure out what bond you got to break. It's a decarboxylation. So the bond you have to break is between, in this case, the alpha carbon and that carboxylic acid functional group. Break that bond and then push those electrons down to the nitrogen. In the next step, just like every other mechanism we've seen, in the next step, take those electrons and push them back somewhere. Make a new bond. And then in our final step, we need to release our product from our cofactor. Step 1, make the bond between the cofactor and the reactant. Step 2, break the bond that you need to break. Decarboxylation, deprotonation, whatever it may be. Push those electrons down to that positively charged nitrogen, which serves as our electron sink. Step 3, push the electrons back up through the cofactor, through what is close to our product now, and make a new bond. Step 4, release everything. That's the same thing with Schiff base, with PLP, and TPP. Okay, they all have the same overall theme. They react a little bit differently, and they allow you to break different bonds, right? So ultimately, they all kind of serve different purposes because the electron sink is a different position away from the bond that you need to break. And that matters because if you try to use PLP here, what you would ultimately find is that you don't really have a place to push your electrons. Okay, the nitrogen is not lined up properly. Okay, so those are the 3 lyase reactions that we've seen where ultimately we can break a carbon-carbon bond because we have a place to put those electrons, right? Which otherwise is typically a hard thing to do. But these cofactors give us a place to put electrons. Make sense? Any questions? All right, so that should all hopefully be a little bit of a review that we talked about on Tuesday. Okay, today we're going to talk about isomerases. Okay, so as you know, isomerases are enzymes that catalyze the conversion of a substrate, right? So basically move a functional group from one place in a molecule to another place, or make a rotation in a bond so that you have a different stereocenter, right? They do something that changes the structure of the molecule, okay? But it's one reactant, okay? Just like everything else, we can break this down into different subcategories. We won't really go into them. Okay, the ones that I want to kind of focus on here are the ones, especially the representative ones that we're going to see this semester. So the first one that I'm pointing out here is an enzyme called triose phosphate isomerase. This is another key enzyme in glycolysis. So once we've split that carbon-carbon bond, right? Aldolase used the Schiff base to break a 6-carbon chain into 2 equivalents of 3 carbon chains. These are the 2 products. These are our 2 3-carbon chains. For both of them to proceed through glycolysis, we need them to be interconvertible, right? So we need them to readily be able to convert between one or another. Okay, and that's what this enzyme TPI does. You might also hear it as TIM. triose isomerate mutase. But so the idea is, and this is actually a really cool enzyme. Dr. Herbert may have talked about it last semester. I know he really likes this one. The reason it's so cool is it's the champion enzyme. It is the fastest enzyme on the planet. Okay, it very, very, very quickly converts an aldehyde to a ketone. That's what it's doing. The isomeration it's catalyzing here is interchanging an aldehyde and a ketone. So it's moving the position of the double bond. Okay, um, it's the champion enzyme in that it's diffusion limited. The reaction is so fast that the maximum rate depends on how quickly the substrate can get into the active site and the product can diffuse out. So it does not obey Michaelis-Menten kinetics. It's the K2 step, right? That conversion of the enzyme substrate complex into products is so fast that we can't even measure it. Like the rate constant, like 10 to the 8th, really fast. So it's a really cool one. Okay. If we look in the active site here, we can kind of get a hint about what matters. What you'll notice is that there are several things that are anchoring it in place, which is no surprise. But what we'll also notice is that there is glutamic acid here that can serve as a general acid or a general base. On the other side, there should be a histidine over there, but it's not showing up, that can really help out. Okay, so question 4 in your activity is going to walk you through how this happens. And the one thing that I want to point out is that in this mechanism, it's going to be initiated by deprotonating a carbon. And that's uncommon, but that's how it starts. Step number 1 is deprotonate a carbon. Okay, so I'm going to give you a few minutes here to go ahead and work through that.